Hello everybody, and welcome back to Algebra 1, Big Ideas. Today, we are talking about a topic that we haven't talked about for a second, which is Unit 5. We started Unit 5 last semester, but there are a couple loose ends that we still need to tie up. So right now, we're on page 159, where 5.6 is. Now, we've learned about linear equations in two variables. Something like, for instance, y equals 3x plus 2. But linear inequalities, while similar, are slightly different. It's the same general idea. We have a y and an x, but instead of an equal sign, we have an inequality symbol. Something like y is less than 3x plus 2. The form of these linear inequalities could be like this. ax plus by is less than c, or ax plus by is greater than c, or you could have it less than or equal to, or greater than or equal to. Those observant among you may recognize this as standard form, meaning if we really wanted to solve for the x and y intercepts, we could do the thumb trick and cover up one at a time. This is what a linear inequality in two variables is. And just like before, the solution is going to be the same. When we ask for a solution of a linear inequality in two variables, what we're really asking for is a pair of numbers, x, y, that work for those numbers. So let me give you a quick example here. And you will need a separate sheet of graph paper for this assignment. Let's take a look over at our sheet of graph paper. And let's say, for instance, I gave you the linear inequality x is less than, well, let's do less than or equal to. X is less than or equal to y. Okay, that's a little bit of an interesting one here. Before we start worrying about graphing things, I want to ask you, is the point 3, 7, is that a solution to this inequality? There's only one way to find out. We have to plug our x into x and our y into y, giving us 3 is less than or equal to 7. So yes, 3 is less than or equal to 7, so 3, 7 is a valid solution. But let's say I wanted to figure out all possible solutions of this inequality. Well, normally what we did is we would have a line graph or a number line, something like this. And when it was just one variable, we would go through, let's say if we had x is less than or equal to 2, we would go through and we would actually graph this by putting a dot at 2, closed circle because of the equal sign, and then pointing an arrow towards all the solutions. But when you have two variables, you go up to 2 dimensions. In other words, you have an x and a y dimension, an x and a y axes. So we need a graph like this to accommodate it. Here's what I want us to do. I want us to start going through and just start putting points at all of the possible solutions for this inequality. X is less than y. In other words, I want us to put a dot anywhere that x is less than y. It's sort of hard to do this systematically, but let me give you an example of how I would recommend doing it. Let's say we start by saying x is 1. If x is 1, what are all the possible y values that are greater than or equal to 1? Well, if x is 1, y could also be 1, right? Because 1 is equal to 1. So 1, 1 is a solution. Y equals 2 would be bigger than 1. 1 is less than or equal to 2. So we put a dot there. And 3, and 4, and 5. and 6, and so on and so forth. Once you figure out all the places where y is bigger than or equal to 1, try it out again with x equals 2. Well, we go through and we find that 2 is less than or equal to 2, 3, 4, 5, 6. So we put those dots in. I want you to take maybe about 5 minutes. Pause the video here, and I want you to go through and finish this little matrix of dots that we're going to create. Again, we're just going to be finding all the places where x is less than or equal to y. Pause the video and fill out your own graph. Look at what we have when we finish up. It's kind of beautiful in a weird way, right? We get that this whole area has a bunch of dots. In other words, the solutions of a linear inequality aren't just going to be on some imaginary line, it's going to be a filled-in area. What we've found is every single number to the left and up from this imaginary diagonal line is a solution. There is a good reason for this, and we're going to talk about it now. This line, this imaginary line where these points go through, has a name. Let's figure out the equation of that line. The line that starts at 0 and goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Well, if we put it into y equals mx plus b form, and we say that our starting point is at 0, our y-intercept is plus 0, and if we go up 1 over 1, that's 1 over 1x. Well, since this is 0, we can just get rid of that, and 1 over 1 is just 1. This boundary line, as we call it, is the graph y equals x. And look at the problem that we had. X is less than or equal to y. It's the same thing, just without the inequality symbol. Bam, like that. This gives us an insight on how we can actually go through and graph inequalities. The first step is to draw out this boundary line. The second step is to figure out if above it and to the left should be shaded in, or below it and to the right, whatever area should be shaded. Let's do another example, this time with possibly a little bit bigger numbers. So I'm going to make another graph here. Let's do an example here with the inequality 3x plus 12y is greater than, let's do greater than 24. Greater than 24. What I want us to do is this. We're going to start by solving for the x and y intercepts because this is in standard form. After that, we're going to go through and graph that boundary line. Here's the deal. By solving in standard form, we know that we can use the thumb trick. So if we cover up our x, we get 12y. 12y is less than 24. And if we divide both sides by 12, we get y is greater than 2. Just like before, when we solved it if this is an equal sign, we can almost imagine this as an equal sign, telling us that our y-intercept is at 2. Now, I realize I made my graph a little bit too small for this, so let me extend it out just a little bit. If I did the same thing for the x's, we would get 3x is greater than 24. Divide both sides by 3, giving us x is greater than 8. So, 1, 2, 3, 4, 5, 6, 7, 8. That's our x-intercept. Normally, at this point, we would then want to connect these two lines together, or to connect these 2 points together with a line. But there's a new rule we got to talk about with inequalities. Remember how before if you had a less than or a greater than symbol, it was an open circle. And if you had a less than or equal to or a greater than or equal to symbol, it was a closed circle. When we're talking about lines, if you have a less than or equal to or greater than or equal to, we just do our normal solid line, just like we did up here. If you have just a less than or just a greater than symbol, you're going to use a dashed line. It's a little different. So here we have a greater than symbol. So we would use a dashed line to describe it. Here we are, and I'm going to use a dashed line to connect these 2 points. Bam and bam. We have just created our boundary line. But now here's the problem. I don't know if I should say that all the points above or all the points below are solutions. The way we find out is this. We take our original inequality, 3x plus 12y is less than 24, and we want to try out a test point. The test point could be any point as long as it's not on our boundary. So let me pick, I don't know, this point right here, -2, 1. Let's find out if -2, 1, when we plug it in, is greater than 24. Well, when we plug it in, 3 times -2, because our x was -2, plus 12 times 1, since our y was 1, and we want to see if it's greater than 24. Well, 3 times -2 is -6, 12 times 1 is 1, and -6 plus 12 is just 6. Is 6 greater than 24? It isn't. So we would say that this is not one of our solutions, which means that the one next to it isn't a solution, and the one next to it. Anything on this side would not be a solution. To show that our solutions are not on this side, we would say that everything up above is a solution. It's cumbersome to put out every single point. It took a while. So instead, we like to lightly shade the area where our solutions are. So our solutions for this one are everywhere on this side of the line. That is the solution to this inequality. What I'd like you to do here is I would like you to pause for just a second, and I actually want you to flip over to page 160 in our notes. And here's what I want you to do. I want you to try to graph problem 7, problem 10. Keep in mind which lines are dashed and which ones are solid. So 7, 10, I want you to graph 15, and I want you to graph 17. So 7, 10, 15, 17. Try these problems out and then check in with a partner to check your answers. We're going to pause the video here while we do that. We'll come back to talk about 5.7. 5.7 is a lot like 5.6. It just sort of takes what we learned and puts it in a different context. We've talked about systems of linear equations. Now we're talking about systems of linear inequalities. It's the same deal. A system of linear inequalities is still just two inequalities on the same plane. The solution is still going to be the pair of coordinates x comma y that works for both inequalities. This is stuff that we've talked about many times before, so I won't go in depth with the definitions. But I do want us to take a look down below at this example here. Would you look at that? This is what your end goal will be for graphing a system of linear inequalities. And it looks complicated and weird. But when we actually dissect this, it sort of makes sense. Let me explain it one piece at a time. This is the inequality, this, I should say, is the inequality for y is greater than or equal to 2x minus 1. It's this solid line and everything shaded to the left of it. The inequality y is less than x plus 2 is everything along this thin dashed line and everything to the right of it. So the inequalities that work for both are in this weird sort of almost kite shape down here. That is the solution of the system of linear inequalities, the place where the shading happens for both. The process is the exact same as if we were just doing it with one. In fact, let's flip over to problem number 5. It says to graph this system of linear inequalities. Now, if you have two highlighter colors, this would be a fantastic time to use them. If you do not, I want to give you warning. Shade lightly. I'm talking lightly brush the paper when you're coloring in. Don't try to go for a solid color. Go for a very faint color. Let's start off by graphing the inequality y is greater than negative 2. Our first step is to graph the boundary line and then shade in the area above or below it, depending. To graph the boundary line, we almost imagine it as if it was y equals negative 2. In other words, what's the y-intercept of this inequality? Well, it's negative 2. We don't have an x here. All we're given is our y-intercept of negative 2, because the y-intercept is a number that's by itself. It's the same as if I was to ask you to graph y equals negative 2. Remember on our Unit 3 project how we had those horizontal and vertical lines? This is the same thing. But we got to graph out the rest of the boundary line. We can't just graph a point. Since our slope is 0, you could imagine it as 0 over 1. But another way to think about it is this. What are some other places where the y value is negative 2? I mean, our point is at 0, negative 2. What's another point that has a y-coordinate of negative 2? Well, 1, negative 2 has a y-coordinate of negative 2, and so does 2, negative 2, and 3, and 4, and 5. All these points along this line have a y-coordinate of negative 2. Turns out that is how we graph the line. The line is horizontal. But before we put it down, I want to ask, should it be a dashed line or a solid line? According to our symbol here, it should be a dashed line. The dashed line, a lot like the open circle, just tells us, hey, our boundary is here, but it isn't actually where things start. It's just where the solution begins. So this is our boundary line. Now we need to figure out if we should have the area shaded above it or below it. To figure that out, we use a test point. And I'm going to use the point 0, 0. That's a fun point to use. If I plug in 0, 0 into this inequality, we get 0 is greater than negative 2. Is that true? Is 0 bigger than negative 2? Well, since it is, 0 is bigger than negative 2, we would shade the area where 0, 0 is. We would shade this area here. I'm going to do it in yellow highlighter, but if you're shading and you're using a pencil, please do it very, very lightly. You'll see why in a second. There we go. So that's that graph settled. But we have another graph to, well, graph. Y is less than or equal to 3x. The process is again the same. We're going to graph it as if it was y equals 3x. Then decide if we have to use a dashed line or a solid line. Then find which area to shade. The graph y equals 3x. What's the y-intercept? There isn't one. So in other words, our y-intercept is at the origin, 0, 0. And if our slope is 3, well, we don't like our slope being a whole number. How can we turn that into a fraction? Anytime you have a whole number, you can turn it into a fraction over 1. So our slope is 3 over 1. That means we go up 3 and over 1 to find the next point. To graph this, we have to ask ourselves once again, is this going to be a solid line or a dashed line? Since we have that equals bar, this is actually going to be a solid line. We've just graphed our boundary. The last thing we need to do is figure out which direction to shade, and we can't use our old faithful 0, 0 as a test point. Is all hope lost? Is this just a lost cause? No. You can use any point you want, as long as it's not on the boundary. I'm going to use 2, 0. But you could use any point, anywhere on the graph. If I plug in the coordinates 2, 0 into this, the y is 0, so we get 0 is less than or equal to 3 times 2. So what is 3 times 2? We get 0 is less than or equal to 6. And is that true? Is 0 less than or equal to 6? It is. It's less than 6. So our goal is to shade in this area. Now here's the trick, y'all. We're shading in the entire area to the right here. So we're shading from down here all the way up here. Again, you shade in the entire area to the right of our boundary line. And what you see is something very interesting that appears. We've created 4 zones almost, 4 areas. In fact, the technical term for this is 4 half planes. Anytime you shade in an area of a plane, we call it a half plane, even though this is more like a quarter, to be honest. In this blank area, notice how there's no shading at all. That means none of our solutions are in there. The solutions to y is greater than negative 2 are not in there, and the solutions to y is less than or equal to 3x are not in there. In the yellow area, and in this sort of green area, we have the solutions to y is bigger than negative 2, because that's where we shaded in yellow. In the blue and green areas, that's the solutions to this line. But the solutions to both are the areas where both shadings happened. In other words, the areas that were shaded yellow and blue. This area here is the solution of the system of linear inequalities. Every point in here works. My outlining was awful there. Every area or every dot in here works for both inequalities. So again, our goals are graph the boundary lines, shade the areas, and see where those areas overlap. If you can find some overlap, you found some solutions. If they never overlap, that means that there are no solutions in that area. Here's what I'd like you to do to wrap up. I want you to try out problem number 6 on your own. Keep in mind, these are going to be horizontal and vertical lines. Afterwards, I also would like you to try out problem number 8. If you would like a challenge, only if you want a challenge, I would recommend trying out problem number 11. So, let's get to it, y'all. We're doing problems, once again, 6, 8, and if you want a challenge, number 11, and then checking with our partners. That said, that is the end of our lesson for today. So, I hope you have a fantastic rest of your day, and I'll catch you next time.